Thank you for inviting me for the talk. So, since all of you are here, I'm sure you all know the story of this last decade. In this last decade, we have made significant advances in the field of AI, thanks to deep neural networks, convolutional neural networks, or whatever you call them. However, if you think, despite all this progress, both our learning and inference paradigm are still quite narrow in scope. So let's look at the learning paradigm. So there are two most commonly used learning paradigms. In computer vision, how we do perform learning is we first download millions of images from the internet. We then label those images with the labels of interest. For example, there's a dog, there's a cat, there's a mushroom, and so on. And then what we perform is supervised and passive learning. It's supervised because humans have supervised and provided labels, and we want the deep neural networks to output the same labels. It's passive because the algorithm or the neural network has no control over the data it is seeing. These are randomly downloaded million images, for example. Now, the second most commonly used learning paradigm is this reinforcement learning paradigm. So how does this work? First, you pick up a task of interest. You then find an environment in simulation mostly. So for example, you're interested in, let's say, Atari Breakout game. Then you engineer the task rewards. So you can either develop your own task reward, or you can use some external task reward, for example, like a scoring function in the Breakout game. And then you perform what is called reinforcement learning. And after millions of iterations, you end up learning a policy function, which given an image or any other state as input, produces what action the agent should take, essentially. Now, even after these millions of iterations, this policy function only works for this task and fails to transfer to a different task, or even fails to transfer from simulation to real, for example. Now compare this to how we as humans have performed learning about the world, for example, right? So let's look at how we have understood about the world in natural sciences. So as scientists, we always first propose hypotheses about the world. So for example, if you're trying to learn about gravity or something, our first hypothesis would be that if we throw the object up in the air, at some point it will come down, essentially. Once you propose hypothesis, you come up with a set of experiment to verify whether this hypothesis is going to be true or not. And then you basically perform this set of experiments and predict whether this hypothesis is true or not. And if it is true, you add it to your knowledge base about the world, essentially. Now forget about natural sciences. Some psychologists have even claimed that even babies use this whole hypothesis, proposal, and verification scheme to learn about the world. So for example, Alison Gopnik at Berkeley has argued that babies are kind of these little scientists which propose hypotheses about the world, and then they try to verify this hypothesis by performing experiments, for example, throwing the blocks in the air and so on. And this is how they learn about the world themselves. And so in the first part of the talk, inspired by this hypothesis, proposal, and verification regime, we want to propose a new paradigm of learning, essentially. So we want to look into hypothesis verification as a way to verify knowledge, essentially. Now, I should point out that hypothesis verification has been a well-known problem in classical AI, but what we are trying to do in this part is formulate hypothesis verification as an RL problem. So our idea is that the agent has to perform some actions, generate observations, and that can help us to verify whether this hypothesis is true or not. So here we want to look how you should perform actions to verify and build knowledge bases, essentially. Now let's look at the other part of the other side of the coin, which is the inference. Now, once you have done your learning with supervised and large-scale learning, you then use your learned neural network to perform inference. And most common way we perform inference is we basically do the feed-forward pass, and we basically get the output of the task, essentially. So let's look at the task of, for example, grasping. Most of the work has looked at this idea of stable grasping. And so the idea is, given an image, you feed forward and you predict what angle, at which angle you're going to be successful for grasping. And this would work for the same object or a same object in a different viewpoint. But when it comes to novel object, an object you have never seen before, this seems to work okay sometimes, but it might also fail to generalize in many cases. And if you have never seen this object category before, then also it's sometimes questionable if this would work. But let me consider even a much harder situation. So generally, for like a object like screwdriver, the prototypical task is twisting of screw. And so this grasp looks fine. But let me ask you, let's suppose our goal was to do the task of hammering with the screwdriver. And now I ask, what will be a good grasp for this to perform? Well, in this case, you want to grasp it at the metal part so that you can hit with the heavy hand, the place where you hold the screwdriver essentially. Now, someone can argue that, of course, this deep network was not trained to perform this task, so it would not generalize to something like this. And it makes sense. And the right solution to this would be maybe is to label the data essentially. And so now the new formulation would be given an image in a task. You have to predict what angle is it going to be successful for that task essentially. But think of amount of data that you need to correct. There are hundreds and thousands of tasks. We humans are pretty creative with the object use. So we can use the same screwdriver for twisting screws. We can use the same screwdriver for hammering. We can use the same screwdriver for taking paper out of the printer and many more things essentially. And so now think of hundreds and thousands of tasks and hundreds and thousands of categories. And you have to label each object with each of the tasks. And this clearly seems unscalable way of, it doesn't seem scalable to collect data for this problem essentially. So how do we humans solve this problem? Well, we know what the task of hammering actually means. The task of hammering means applying a force. It needs to apply the force with some heavy volume. And we also know that the screwdriver can be somehow mapped to a hammer, where the metal part becomes the handle and the handle part becomes the heavy hammer head essentially. And so in this case, our knowledge of what a hammering task looks like and how a screwdriver and hammer are related to each other in terms of instruments become kind of very, very critical. So in the second part of the talk, I'm going to talk about this way of using knowledge as a way to perform task-oriented grasping. Here, the grasping has to be performed for doing a task itself. And we know that a simple feed-forward and end-to-end learning is probably not going to be a feasible solution because you need lots and lots of data essentially. Okay, so this is what my talk looks like. So I'm going to talk about this knowledge action cycle that actually exists. So the first part of this cycle is we can use actions to verify knowledge and build knowledge bases essentially. And the inverse, which is we have to use knowledge to perform actions themselves so that they can generalize and we can do novel tasks and novel categories that we have never seen before essentially. Okay, so let me start with the first part of the talk, which is the hypothesis verification problem. Okay, so the problem setup here is given a world and a hypothesis. So we are not going to deal with the first part of this learning paradigm where you first propose hypothesis and then you verify them out. We are assuming that the hypothesis is given to us, and the goal of an agent is to verify whether this hypothesis is true or not. So for example, in this grid world, the hypothesis we are given is when you're at the crafting table, you have a stick, and then you craft and the torch is made. So to verify this hypothesis, the agent has to take actions. So it has to first go and pick up the stick, then it has to go to the crafting table, then it has to perform crafting action, and then see what happens essentially. If a torch is made, then the hypothesis is true. If the torch is not made, then the hypothesis is false. So this is the problem setup that we are looking at. Let's look at how we can formulate it as an RL problem. So if you think of a world, like a grid world, the state space we have basically represented by a state space, which is usually a grid, the action space, which is up, down, craft action, and so on. The world is guided by a transition function, which is determined by the rules of the world. And overall, this becomes a Markov decision process. If you're looking at one world with set rules, this becomes a Markov decision process. However, we are going to assume that we have different worlds with different rules. So there's a world one, which has a rule, which is like when the red switch is on, the door opens. And then there's another world where we have the rule, which is that when the blue switch is on, the door opens essentially. So our problem setup actually is we do not have the full information. We do not know which world we are in, which world the agent is spawned in. And so we have to figure out what are the rules of the world. And that is why we need to take actions to basically figure out what are the rules of this world and generate observations which can help us figure out what are the rules of this world in this scenario. Now for generating hypothesis, given the rules of the world, we basically generate the hypothesis from those rules. And we are going to ensure that the hypothesis has a probability of being true, like with 0.5% probability. So we have both positive and negative hypotheses essentially. And specifically for the environments, we are going to look into 4 different environments. The first environment is the color switch environment, which I just talked about. The second one is push block, where you push a block to switch open or close the door. The crafting environment, and the cart pole, which is a more continuous action environment essentially. Now, since we are trying to formulate it as an RL problem, we need to define the reward function, right? And so the reward function here is simple, that if your final answer matches the ground truth, you get +1 reward. So for example, if you say that the hypothesis is true and it is indeed true in this world, then you get +1. If you say it's false and it is indeed false, you get still +1 reward. On the other hand, if you say true and it's false, then you get a -1 reward essentially. And if you're not predicting anything, you're just continuing to take actions to generate more observations, you do not get any reward. It's a 0 reward essentially. So just to highlight it further, so let's say we are in this world and we have a hypothesis that when the red switch is on, the door opens. And in this world, the rule is that the blue switch opens the door. So the ground truth here is false. So the agent starts taking actions. So it moves towards the red switch, then it toggles the switch, and it basically generates the observation. And based on these observations, it predicts that this is a false statement. And so because this is indeed a false statement, it gets a +1 reward. On the other hand, if it would have said that it is a true statement, it would have gotten the -1 reward. So this is how the reward function looks like. So what we need to train is this policy network. So what does this policy network do? The policy network needs to take actions that can help generate observations, which can help you predict whether the hypothesis is true or not. So for example, going to our original example, we need to pick up the stick and then we need to move to the crafting table. These are the kind of actions we should take because these are the actions which are necessary to generate the observations which can help us predict whether the hypothesis is true or not. So this is what our policy function looks like. Given the hypothesis and the current observation, it basically predicts what action you take next. And the actions are configured so that you can generate the right observations that can help you predict whether the hypothesis is true or not. But apart from learning the hypothesis function, the policy function, policy network, we also need to learn a prediction network. Now this prediction network takes as input the hypothesis that you're trying to predict whether it's true or not, and the observations that you have generated by taking actions essentially. And now it basically has to predict whether this hypothesis is true or not. So if the torch is made, you will try to predict it's a true hypothesis. If the torch is not made, you will say, okay, it's a false hypothesis essentially. Now, if you think of what we are trying to do, this is a dual optimization problem. So if you have a wrong policy function, if you're not able to take the right actions, for example, if you're just moving around in the free space, your prediction function cannot do a lot, right? I mean, if it doesn't have the right observation, it cannot predict whether the hypothesis is true or not. On the other hand, if you have a bad prediction function, the policy function will never get the good reward. And so it will never be able to learn properly, essentially. So now we have this dual optimization problem. And that is why if you try standard RL approaches, like off-the-shelf RL approaches like PPO on this problem, it completely fails to work. And so we need to somehow get out of this problem itself. Well, our solution is simple. Can we use some of the structure of the world to pre-train our policy function essentially? And if we can pre-train a policy function and initialize the policy function in a proper manner, then hopefully it can guide us to the right solutions when we are training it for the hypothesis verification task. So what could be a good pre-training reward to pre-train this policy function? Well, the observation that we make is that there's a big set of hypotheses that you can have to verify in the world, right? But the small subset of this big set has some very nice structure. And the specific structure I'm talking about is this triplet structure of precondition, action, and post-condition. So this is the idea that if you are at these conditions, if you satisfy condition, like if you toggle the switch or if you turn the switch on. So if you're at the switch, then you turn the switch on, that is the action, and then the post condition is the door opens. So a lot of these a good subset of this hypothesis can be broken down into this triplet structure, and we can use this triplet structure to build a pre-training reward, essentially engineer a new reward, which can help pre-train the policy function such that when we are fine-tuning the policy function for a new hypothesis which does not have even this triplet structure, it will work uh, to learn to how to optimize for that, essentially. Now, the solution what we are going to do is how exactly are we going to use the triplet? We are going to reward the policy for attaining precondition. We are going to reward the policy for attaining post conditions and so on. And that way, we are basically going to learn how to do the right actions which are going to help us move in the right direction, essentially. So the first pre-trained reward is if you have a precondition, for example, the red switch is on, you get a reward if you attain the precondition, like if you attain the precondition, essentially, like if you toggle the switch, the state of the red switch changes, you get a reward which is a plus C. Similarly, you will also get a reward for attaining the post condition. So in this case, the post condition is the door opens, and when you actually move to the blue switch and you toggle the door, you get a new reward for getting the door opened, essentially. And so we first retrain our policy with these two rewards, and then we try to fine tune it for other hypotheses, essentially. And so here are the results that we get. So as I talked about, that the RL baseline or the random action baseline or even no action baseline, like you just keep observing the world and you try to predict whether the hypothesis is true or not from the static world, essentially. All the three baselines really fail to solve this problem at all. On the other hand, if you pre-train a policy, then you fine tune it. It seems to work reasonably good in all the environments. But even if you actually use the fixed policy from pre-training, and we do not basically fine tune this, it seems to also work reasonably good, especially for the setup that it has been trained for, essentially. You could try to use some other pre-training reward. For example, you could reward for changing, like going to any named item or going to any item and changing their conditions and so on and so forth. But it turns out that the pre-training rewards, using the triplet structure is kind of critical, and that helps you to learn a much better pre-training policy, essentially. Now, just to highlight that this is a really, really hard problem. We also tried this setup where we assume that for example, the prediction function is learned, and we are just learning the policy function. So on the left is that setup. And you can see in that setup, we end up learning a good policy function. So on the other hand, if we assume that the policy function is good, then we just have to learn the prediction function. Again, we end up learning a good prediction function. So the hardness of the problem comes from this dual optimization problem, and that is what is that is why we need to use a structure to break this, like guide this in the right direction, essentially. Okay, so this is the first part of the talk, where we basically formulated hypothesis, this classical AI problem of hypothesis verification, as an RL problem. And I think what is interesting is this approach of using some structure in the world to initialize the policy, and then basically transferring the policy to even hypotheses that might not follow this structure. So if you fine tune on the pre-trained function on this, on the hypothesis which do not even have the structure, you might still end up learning a good policy function, essentially. Okay, so in the first part of the talk, I talked about how actions could be critical to learn, verify knowledge, and basically build knowledge bases by a verification process, essentially. In the second part of the talk, I want to look at inverse. I want to see how knowledge can help us to perform actions that can actually generalize. I mean, and generalization is a critical term here, right? Now, what we are trying to look at is the task of task-oriented grasping. So generally in the past work, we have seen a lot of work in stable grasping, but we know that whenever we grasping is like an intermediate task, right? Our goal is to perform some action and so on. And when it comes to humans, we do not only perform prototypical actions. So for example, we could try to label the prototypical grasp for all objects and then learn a function for prototypical grasping. So for example, you should always grasp screwdriver from the handle, or you should grasp the wine cup from the stem, and so on. But humans are not just using objects for prototypical actions. We are pretty good at using objects for creative uses. So for example, a screwdriver could be used for hammering, as I just said. It could be even used for taking out the printer. It could be used for cutting things, for example, using a sharp end and so on. So it's so what we're interested in is this task of given an object and the task you want to achieve, what would be a good grasp that the robot or the agent should perform uh, to achieve that task essentially. And this is the problem that we are trying to look at. Now, I think it's worth pointing out that there has been some past work on this task-oriented grasping or semantic grasping, and we are looking at both. So, for example, ContactDB looks at the semantic grasping, like how do humans prototypically grasp objects and so on. So this is mostly for prototypical grasp. On the other hand, SG14000 is a dataset which looks at more task-oriented grasping and so on. TogNet looks at a more synthetic data for grasping at a larger scale and so on. However, all these data sets and all these approaches have an issue. Like they are only looking at very small number of tasks, like 2 tasks or 7 tasks. On the other hand, we want this data set to be large, right? I mean, we want to really see how you can use screwdriver for cutting, for example, and so on. So what we ended up doing was we first ended up collecting the largest grasp data, task grasp data set. So here, given an object and a task, you have to predict what grasp is going to be successful for using that object for that task, essentially. So our data set is order of magnitude larger than any of the approaches. So for example, compared to both ContactDB and SG14000, we have 10 order of magnitude more grasp that are labeled. It is less compared to TogNet, but ours is real and that one is synthetic. Number of tasks, again, we are order of magnitude more number of tasks. We have 56 more tasks, whereas the next closest one is SG14000, which has only 14 tasks that are captured. But what I'm going to argue is that just collecting the large scale data is not going to solve, right? I mean, if you think of number of object categories and number of objects in the world and multiply it by number of possible tasks that you can use these objects for, there's no way you can end up collecting this large scale data essentially. And so what we're interested in is developing a framework where you can use the knowledge or the relationships between these objects, tasks, and even the hierarchy of objects somehow to end up solving the problem with not, I would say, a small amount of data, but by reducing the amount of data. How much can that help in reducing the amount of data specifically? So before I go into the approach of how to use this semantic structure of the world to solve this problem, let me first talk about the data set. I think it's a very nice data set and I would like to publicize it a lot because I think this is one of my feeling is that this is going to become one of the coolest manipulation data sets in the coming, because it has semantics and everything. So the task graphs data set is basically, think of it as having 3D point cloud data, and then for an object, and then you have, it basically has to have graphs which are going to be successful for a task. So for example, for painting task, you should be handling the roller form, the handle, and so on. How do we get it labeled? Well, first we ask humans whether this object is even possible to do the task with. Like, can you pour something from a mug? Yes. But can you use a mug to cut something? Probably no. So first we do this filtering based on simple yes and no question. And then once we know that this object can be used for pouring, we sample a lot of stable grasp for this object and then ask humans which of these grasp are going to help be okay for pouring and which grasp are not going to be okay for pouring, for example. And that is how we ended up collecting 250,000 grasps for this task. One of the cool thing about this data set is that we have resolved the objects and tasks to their WordNet synset. So basically we have the semantic information with us. And we also have, apart from this WordNet mapping, we also have explicit knowledge, for example, the knowledge graph, between like the relationship between objects and tasks, and we have implicit knowledge, the word-to-vec embeddings for both the tasks and the objects essentially. And so here is what our data sets looks like. As you can see, we have ladle for pouring, so you should grasp it from the handle. If you're using a mug for hammering, you should not hold it from the, you should hold it from the thing. Ball for scooping, and so you can see, like if you're trying to like we have this wide variety of tasks for wide variety of objects labeled in this data set. Now, formulating the problem and talking about how knowledge can be critical in solving this problem, especially because there's no way you can scale up the data. So our problem is to predict what grasp is going to be successful given the point cloud and the task that you're trying to use the object, point cloud of the object and the task you're trying to use the object for. we want to build on this lot of work in stable grasping essentially. So we've basically factorized the problem into two parts. First, we have to sample a stable grasp, and then you have to predict whether the stable grasp can be used for attaining the task or not. So we have basically factorized our problem into two different terms essentially. And so this is basically what our setup looks like. Given an object, the 3D point cloud of an object, we sample lots of stable grasp. Given us stable grasp, we basically now have a point, like we generate the point cloud for the stable grasp and the object. And then we basically can encode it using the grasp and object encoder into one-dimensional, d-dimensional vector. And that is used to initialize the knowledge graph essentially. So we are basically going to initialize a knowledge graph which has objects and tasks as nodes, and also the 3D point cloud representation of this grasp essentially. The object nodes are initialized with the word2vec vectors, and the task nodes are initialized with 0 and 1. So if you are trying to use this, evaluate this grasp for pouring, the pouring node turns 1, and all the other task nodes turn to 0. And now you basically start some simple message passing using graph convolutional network. And the idea is that we can develop some latent representation which has this task-based score hidden at the node essentially. And then you just learn an decoder function which basically looks at the representation of this grasp in context of the object category and the task that you're trying to use for, and then it evaluates and gives you the score whether this is going to be successful, whether this grasp is going to be successful or not. For evaluation, we use 3 different ways. First, we are going to, we want to test the generalization. That is, I think, the critical thing here, right? For standard, like feed-forward inference could be used, but that fails to generalize is what our claim is here. And so the 3 generalizations, 3 ways we can test generalization is, first, you can have objects. You might have seen objects from the same category, but this is a completely new object. So this is the instance generalization. Then you might have a new category of object that you have never even seen before. And so now you want to make it work for that. And then you have a new task that you've never even heard of this task before, and you somehow need to make it work. You might still have the information that these 5 objects can be used for these tasks and so on, essentially. The first baseline that we are comparing to is the random baseline. The random baseline is just taking a random stable grasp and seeing whether it's going to be useful for task or not, essentially. The semantic grasping network is like an end-to-end network, essentially. You can also combine semantic grasping network with a word embedding network. And finally, GCN grasp is our approach. And as you can see, our approach performs really well, beats all the baseline, but especially for the task setup, right? For a completely new task, this works, which is the hardest difficulty level in some sense. In terms of relationships, like object-task relationships are the most critical to make it work. But the WordNet object hierarchy node relationships are also critical, especially when you're trying to generalize to completely new category of objects, essentially. And then what we did was we also did some test on some real robot. So for example, for sorting a pen, you hold it from the handle, and we basically sample on the grasp and see if it works. For hand over the tongs, you basically pick it from the tong. For the scissor, you pick it in the middle part. So because you have to hand it over, so you cannot pick it up from the handle and so on. Okay, so in the second part of the talk, I talked about the other part of the knowledge action cycle, right? So in this part, basically knowledge can help in generalization. It could be generalization to completely new instance of object, a completely new category of object. And what I'm most excited about is completely new task for this. So you have never even have had any data for this task, and still it could generalize to this new task, essentially. Okay, so in this talk, as I talked about this knowledge action cycle. I talked about how actions can be critical to build and verify and build knowledge. And I also talked about how knowledge can be critical to learn action policies that will generalize to new instances, categories, and tasks themselves. All right, and in the end, I would like to thank all my co-authors who have basically played the great role in these papers. And thank you.